To do a hypothesis test for a matched pairs study, there are two ways that we can write our hypotheses. We can write it as a single parameter mu sub d, which is the mean of the differences extended to the population, or we can make the statement as a comparison of two means, because it is valid to say that we're comparing mean estimates at Jocko's to mean estimates from other garages. We're just doing it in such a way that works with one parameter. So this first model is what we would recommend. This is best for a matched pairs study because you really only have one data set, you have one variable in your data set, there's only going to be one x bar that you're working with, and so your parameter will match your statistic in this case. So this is the best way for matched pairs, is to work with this mu sub d. This here is working with a difference of means. This is like saying mu1 minus mu2 equals 0. So this is a difference of means. And this is okay for matched pairs or for two independent samples. So both of these are valid ways of stating hypotheses in a matched pairs hypothesis test. However, we definitely need to switch over to one variable thinking if we have matched pairs. So our standard error comes directly from the standard error formula for one mean. Recall, for one mean, we had that the standard error is s over the square root of n. This is the same exact formula, but it's using s sub d as the standard deviation of the differences. And for one mean, we also had x bar minus mu naught over s over square root of n. So instead of x bar, we now have x sub d bar, or x bar sub d. Instead of mu naught, we now have 0, because our null parameter is always 0 if we're doing a matched pair study. And in place of s, we now have s sub d. It really is the same formula, just adapted to this situation. So these are the two formulas we would use for hypothesis testing, or really we would use the second one, T. So we have descriptive statistics here for the single quantitative variable, difference. And this is difference Jocko's minus other. We have a mean, a standard deviation, and an n, and these are the three things we need for a hypothesis test. So that sample size is my n, that mean is my x bar sub d, and that standard deviation is my s sub d, because all of these already apply to the column of differences. So in the example we looked at first, we used a randomization dot plot just so that we could ignore the details of what formulas might go into it and not get bogged down in that. But we're going back to a distribution theoretic approach now. So our T statistic, which is x sub d bar minus 0, we don't really have to write, over s sub d over square root of n. Looks like 115 divided by 124.833 over the square root of 10. And it can't be overstated the importance of making sure that when you enter this into your calculator, you are putting parentheses around your denominator if you do the whole thing as one statement. Otherwise, the order of operations is going to be misinterpreted. We want to make sure that is division in the denominator. So it's like a double division that we're doing here to calculate this. So let's bring in a calculator and do 115 divided by open parenthesis 124.833 divided by 10 square root close parenthesis and then equals to get 2.913. My hypotheses, recall, were the null hypothesis mu sub d equals 0, the alternative hypothesis mu sub d is greater than 0. So what this would look like when I put together a curve of a t distribution, a bell-shaped curve centered at 0 with 115 as my sample statistic, but I know that that's about 3 standard deviations away from the mean, so it's pretty far out here. And then I'll fill in that right tail. So for the p-value, we can either use table A or stat key. Let's go ahead and use table A. The p-value is between, let's see what two values it's between. So first of all, to go into table A, we need a degrees of freedom. There are 10 data values, and therefore n minus 1 is 9. We have 9 degrees of freedom in our t distribution. And going to table A with 9 degrees of freedom, I can see that the value 2.913 is between 2.821 and 3.250. Coming up to one tail area, I get that my p-value is between 0.005 and 0.01. So similar to what we found with the randomization dot plot, this does look like very strong evidence. Same conclusion. Very strong evidence, ... right? We've already said what we have very strong evidence of, so we won't write it again. But we see that the distribution theoretic approach gets us the same result. The nice thing about matched pair studies is that there isn't really anything new in them technique-wise. We just turn everything into a single variable study and write our hypotheses in terms of one parameter, use all the formulas we've already seen for one quantitative variable, and the real trick to this section is just getting used to thinking about the distinction between two independent samples and a matched pair study.